Hi, everybody. Welcome back to another lecture of artificial intelligence. So we've always finished the lecture yesterday. There are just a few more things to discuss. So as we discussed yesterday, computational complexity for constraint satisfaction problems is much reduced when we have a tree structure. So the first idea was that we guess the values of a few nodes so that the remaining constraints graph becomes a tree. Another idea that we were not able to discuss yesterday is that we kind of construct a super tree, and the super tree has a tree structure. So you see these nodes consist of sub problems. So here portions of the constraint graph, and this is then assembled into these super nodes, and these super nodes form a super tree. So how does this have to be constructed? So every variable xi appears in at least one subproblem. So if in the original problem you have all these nodes, Western Australia, Northern Territory, Queensland, and so on, each of those nodes has to appear somewhere in these subproblems. The next constraint is that if variables xi and xj are connected in the original problem, they must be connected in at least one subproblem. So for instance, if here we have Queensland is connected with Northern Territory, North South Wales, and Southern Australia or South Australia, then Queensland also has to be connected in some subproblem with Northern Territory, South Australia, and North South Wales. And finally, if a variable appears in two subproblems, it must appear in every subproblem along the connecting path. So for instance, if you look at South Australia, which appears here and here, so it also has to appear in all the super nodes in between. And you can check these three criteria, which are all fulfilled. So this is a valid super tree. So now what we do, we solve each problem independently, each subproblem. And if any of these subproblems has no solution, we know that the entire problem has no solution. So we can quickly make this decision. If we can solve all the subproblems, then we have to construct a global solution as follows. So let's start with solving the first subproblem. So in the example, the leftmost subproblem consisted of Western Australia, Northern Territory, and South Australia. And now here you see all possible value combinations that are feasible. So in each of these combinations, each region has a different color. Okay, so this is the first step. And then we need to find solutions that are shared with the neighbors. So if we look, for instance, as a possible solution for this leftmost node was Western Australia is red, South Australia is blue, and Northern Territory is green. And now you look at all possible solutions of the next super node, which is consists of these solutions. Then you see, okay, we have to have a matching solution. So in the previous super node, Western Australia is red. Western Australia doesn't appear here anyways. So this is trivially fulfilled. But South Australia is blue. So we can only look at the solutions where South Australia is blue. So which are the bottom two. And Northern Territory has to be green, which is only the case for the last solution. So then this solution and this solution are feasible because, of course, you cannot choose different values in this super node compared to this one, because once you made a decision for South Australia, you have to stick with this decision for all the other nodes. And now we've seen how we connect two nodes, and now from this node to the next node, it's always the same. So this has to be repeated over and over again. Okay, good. So finally, here's an overview of all the methods we have learned for constraint satisfaction. So first of all, we had to decide which variable to select first. And there we learned two heuristics. One is minimum remaining values. So you pick the variable with the least remaining values that fulfill the constraints. This was not possible, for instance, if you start from scratch with a new problem, then you need the degree heuristic. The degree heuristic chooses the variable with the most constraints. However, the degree heuristics can also be used later on and doesn't is not only useful when you start, but also later on when you perform the next inference. Okay, then after we've selected the variable, we had to choose which value we want to choose next. And there we use the least constraining value heuristics, meaning that we always choose the value of a variable that constrains the connecting variables as little as possible. So this is sufficient for search. However, when you just use pure search, then it might be that you have to backtrack, and to avoid unnecessary backtracking, we can use inference to foresee whether a certain choice will result in an infeasible problem or not. And there we looked into two problems: forward checking and arc consistency algorithm. So forward checking just looked at the neighbors, and the arc consistency algorithm also looked at the neighbors, but then also from the neighbors constructed the next arcs so that it propagated through the complete graph. And finally, we looked at the problem structure. We've seen that tree-structured problems have a big computational advantage. So we use conditioning to guess values so that the remaining graph becomes a tree. Or, as we've just seen, we can construct a super tree, which is called tree decomposition, sorry. So to sum up, constraint satisfaction problems are required to evaluate variables such that all constraints are fulfilled. Backtracking search is the only search technique that makes sense, and it's basically a depth-first search technique. And inference can be interwoven with search. That's special when you look at constraint satisfaction. Now today we'll start with logics. Then inference is the only method that we will use. So as I mentioned before, constraint satisfaction is kind of a nice bridge between search techniques and logics. We learned the minimum remaining value and the degree heuristic to choose the next variable. And we've learned the least constraining value heuristics to choose which value to choose next for a given variable. And we have seen that the complexity strongly depends on the structure. So if you have a tree structure, we have linear complexity, and this can be realized by conditioning. So guessing values in the remaining graph is a tree, or tree decomposition, as I just mentioned, with the super tree. Okay, so that's it. Now we can start with the next lecture. Let me just check if there's any questions so far. No, so it seems that everything is fine. Okay, so as I already said, today we're going to start a new chapter which covers aspects regarding logic. So today we look into propositional logic, and then into first order logic, which is of course more complicated, and then we have another lecture on inference of first order logic. Propositional logic is not so complicated. That's why we have the modeling or the formulation of propositional logical sentences and the inference of propositional logic in one lecture. For first order logic, this is split into a lecture for the language and a lecture for the inference mechanisms. So how is this lecture organized? I'll first introduce you to the Wumpus world, which will motivate the use of logics. Then we'll talk about logics in general, and then about propositional logic, which is probably the easiest logic you can imagine. And then we will perform theorem proving using propositional logic. And one aspect will be proof by resolution, and the other method will be proof of horn clauses. So horn clauses are a special case. Proof by resolution is powerful enough to prove the correctness or falsify any propositional logic sentence. So the content of today's lecture is fully covered in our AI book by Russell and Norwick in the section Logical Agents. And as always, here's the list of the learning outcomes, which are of course again relevant for the exercise and the exam. First, you understand the difference between a knowledge base and an inference engine. So that's what we'll discuss on the next slide already. You understand the difference between syntax, semantics, and models. If you're studying computer science, you know this already anyways. You understand the difference between satisfaction and entailment. And you can create and evaluate sentences in propositional logic, which is not very difficult. You can create truth tables and sentences in propositional logic. Also, this is something many of you have done before. You can apply inference by enumeration. You understand the concept of logical equivalence, validity, and satisfiability. This is something that maybe not everybody of you knows. And you can systematically apply theorem proving given a set of inference rules. So we will have a fully automatic method that can solve any theorem stated in propositional logic, which is really exciting. And you can apply proof by resolution, which is a specific technique. And in order to do that, you have to convert a sentence into conjunctive normal form, which is very mechanical. So once you know how to do this, this is always, if this comes up in an exam, this is always easy to get points here. And finally, you can prove correctness of foreign clauses, which is a special case of propositional logic sentences by forward chaining and backward chaining. And we'll also discuss the advantages and disadvantages of both techniques. Okay, so first of all, what is a knowledge base? It's typically a set of sentences in any formal language. It could also be SQL table, so essentially a database, or it could be a list of statements in first order logic or in propositional logic. So this knowledge is usually domain specific. Usually you focus on a certain domain. If you want to build a robot, and the robot should work in a household, then you need to tell the robot what is a kitchen, what is a stove, what is a kitchen sink, and so on. As you've seen with the pancake robot. And then the robot has an inference engine, and this inference engine is actually usually independent of the knowledge. So this is a general purpose engine which can take the knowledge and create new knowledge. And already today we'll see how this can work. So now there are several possibilities to gain knowledge. So the first one we know already because I've just mentioned that you can use inference, which makes it possible to derive new knowledge from old knowledge. So if you have some mathematical theorems, by combining these theorems, you might find a new one that you can then use to prove other things again. So what other methods do we have to gain knowledge? Maybe again, please just type it, or just also you can also use the audio to say something. Right, sensors, good. We can just observe the environment and obtain knowledge. That's a very good idea. There's one other very trivial way of gaining knowledge. Just think of how you can gain knowledge yourself. It's just taking database, right? Taking knowledge from outside, let's say from Wikipedia or from a library or something like that. So that's the declarative approach. Knowledge is added from outside by providing knowledge, or perception, as you mentioned, you can just observe the environment. And agents can be viewed in two different, so these knowledge-based agents can be viewed in two different forms. One is at the knowledge level, where you just look at what they know, regardless of how it's implemented. So for instance, if you want to say the kitchen has 5 cupboards and there are 20 knives in the kitchen, then you can implement this in C++, in Python, or you can have an SQL database, something like that. But no matter how you implement it, the knowledge is the same. Or you can look at this from the implementation level, where you then care about the data structures in the knowledge base and algorithms that manipulate them. In this lecture, however, we will focus on the knowledge level. So we will discuss everything independent of whether it's implemented in a certain programming language or not. Okay, so to make this a little bit more fun, we'll discuss many concepts in the Wumpus world. So imagine you're an explorer, you go into a cave with a lot of rooms that are connected. And when you're close to a pit, you feel a breeze. So it's very dark, you cannot see the pit. And so you have the breeze in the neighboring rooms. And if you ignore the breeze and step further, then you just fall into the pit and you're dead. Also, the Wumpus is in the cave system. He looks like a very happy fellow. However, he's actually very hungry, hasn't eaten for a long, long time. You can see also that he has 2 very sharp teeth. And even though you might be very nice to him, if you enter his room, he will just eat you. So this is, you have to be really careful. And he's already awaiting you happily, putting his arms into the air. And also, because he has no bathroom, he smells quite a bit. So if you enter a room that has a stench and you smell something, then you know in the neighboring room is the Wumpus. So then you ask yourself, why am I even entering this cave system? The reason is that you know there is gold in one of the rooms. So here next to the Wumpus is the gold, but it can be anywhere. And you just see the gold when you're in that room, and then you can pick it up and take it home. And if I'm not mistaken, this has been realized as a computer game many, many, many years ago. You can imagine like you can browse these rooms with arrow keys and try to make as many points as possible. So these are just things I've already mentioned. So now we have our first tweetback question. So let's say you want to search to solve this problem using search. It doesn't matter which search technique you use, depth first search, breadth first, uniform cost search, whatever. The question is, does a pure search technique exist? So that we just want to know whether one exists at all. Does a pure search technique exist so that we arrive at the goal without getting killed by Wumpus? So this is a tweetback question. Just answer with yes or no, and then we'll see whether you were right or not. So questions about the link. The link is at the top of the chat. Here's this again.
Okay, so about 55% thinks no.
Okay, so it's not a clear vote, but yeah, we have a small majority for no. So let's keep that in mind. Let's further discuss this Wumpus world a bit. You can use the piece description from the first lecture. So there's a little bit of a repetition. So it stood for P stood for performance. So if we find a gold, we get 1,000 points. If we're dead, we lose 1,000 points. We lose 1 point per step and 10 points if you use an arrow. So we can actually shoot an arrow. So the E was for environment. So what's the environment? So squares adjacent to Wumpus are smelly. So that's what I already mentioned. Squares adjacent to pits are breezy. Also that I mentioned glitter if and only if gold is in the same square. Shooting kills Wumpus if you're facing it. And shooting uses up the only arrow you have. And grabbing picks up gold in the same square. So you have to grab the gold. You can also release it, but doesn't make so much sense. So the actuators are left turn, right turn, forward, grab, release, and shoot. And S stood for sensors. So you can feel the breeze, see the glitter, and smell the stench. Okay, so now we can also characterize the environment. This is also a repetition of the second. So the second lecture actually was on intelligent agents. So observable. Is this environment observable? You can just type in the chat what you think. Yes, most people say no, and that's okay, because you only have partial observation. You don't see everything going on. Otherwise, it would be easy. We would see the Wumpus would never enter this room. Deterministic. Is it deterministic? Yes, everybody says yes, that's correct. Every action we perform leads to a state that we know will happen. Episodic, actually, it's not episodic because if we change something, let's say if we grab the gold and release it somewhere else, we change the environment. So it's a sequential environment. And yes, it's static because if we don't do anything, nothing happens. That's why it's static. And discrete, yes, there are just finitely many states because you have finitely many rooms, and there's in these finitely many rooms, each room can be just a pit, the Wumpus, or the gold. It's single agent, yes, because Wumpus is not really acting, he's just there. And once you enter his room, it's bad, but it's essentially considered, as it's written here, a natural feature. And the main challenge, of course, is that you have this partial observability, and you probably need some reasoning to make good decisions. So let's look at how we would actually act in such an environment. So we've entered the first pit, 1, 1. So we use a coordinate system. The first number is always for the x-axis, which is from left to right, and the second coordinate is always on the y-axis, which is from bottom to top. So we have no sensation here. So everything is fine, and we make a decision, go left. So now we feel a breeze. So what does it mean? It means in the neighboring rooms could be a pit. So in this room or this room, it could be a pit, but we don't know where. So what would be a good next action? Yes, we go back, exactly. We go back and we check out the other room that we haven't visited yet. And there we have perceived the stench. And so that means that the Wumpus could be somewhere. So now that we have a stench here, can we say exactly where the Wumpus is, or do we have to check further? Yes, people say yes. Can you maybe type the coordinates? First one number is x coordinate, the second is y. 0, 2, yes, if you start with 0, so we start with 1 here, but 0, 2 would be this one, yes. So Wumpus has to be here because if the Wumpus would, so potentially the Wumpus could be here or here, but if the Wumpus would have been here, we would already have smelled the stench here. So then the Wumpus can only be in this square. And also what we know, because in this room we didn't feel the breeze, we know, okay, the pit isn't here and the pit has to be down here. And then of course the natural choice is to avoid the Wumpus, so we go right. And then again, we don't smell anything, and because of that we can go up. And there we have, of course, a breeze, so there's another pit close by. We see the glitter, and we perceive the stench, so we know the gold is in this room, and pick up the gold and leave. So if you would have done this via search technique would have explored a lot of children, or would have created a lot of children. And then one of these nodes that you would have created would have been a node where the Wumpus is, and only after you have entered the room, you would have realized, oh, this was a bad idea. So that's why most of you were right. So if you use this pure search technique, you cannot ensure that you will get killed. So you need additional reasoning. So you need some logics. So there's a question, why wouldn't we go further right after avoiding the Wumpus before last step? You mean why we didn't go here? Yeah, we could have done that as well. So we made the decision to go up, but right would have been also fine. Okay. So next tweetback question, search does not prevent us from getting killed, as I've just mentioned. And the question is just, is it possible that even by using logic, we get killed? This is a little bit of a tricky question, but yeah, please vote. Yeah, please use the tweetback.
So about 80% chooses yes.
Yes. Can anybody say in which situation we could still get killed? Maybe that, please type in the chat. Wumpus corners as overlapping wheels. Yeah, the first move. First move is the correct answer. So if the Wumpus would be in the first room, so we enter the room, then we get killed immediately. But of course, as I said, because this is a computer game, if you say we exclude the situation where the Wumpus is in the first room, then you can move in a way that you will never get killed. This is just this one corner case we have here. Okay. So now what we would like to do is all this reasoning that we have done now by ourselves, we would like to fully automate. In order to do that, we need some basics. So as I said, many of you might be familiar with these basics, but some of you aren't. So first of all, we need to tell you what a syntax is. It essentially just specifies how sentences are correctly formed. And we're explaining this using ordinary arithmetic. Since that's something that everybody is familiar with. So x plus y equals 4 is a feasible arithmetic sentence or statement. So this is fine, it's well formed. However, x for y plus equal is not. So this would be the syntax here would not be correct. But just by writing a formula in a correct way, it doesn't mean that you know how you have to interpret this formula. So that's where you need the semantics. It defines the meaning of a sentence. That means when a sentence is true or not. So for instance, if you have x plus y equals 4, x plus y equals 4 is true for x equals y equals 2 and false for x equals y equals 1. So of course, we are very much trained on ordinary arithmetic. We know what this means. But if you define a new logic, you first have to specify what certain symbols and certain operations mean before you can really work with that. We will do this also for propositional logic. Also there it will seem quite meaningless initially, but the more complicated the logic is, the more it makes sense. So for instance, in autonomous driving, we use a lot of temporal logics, and there it makes sense to first define the semantics, because otherwise it's unclear what the meaning of the formulas is. And finally, we have to talk about models. And models, the word model is used in many different disciplines. So for instance, if you are studying fluid dynamics, then a model could be a scaled down version of something in a wind tunnel. So you want to just analyze the system in a different, not the original thing, but a model of the real thing. This could also be a simulation model. In our case, we mean that these are instances which evaluate sentences to true or false. So for instance, if we have X men and Y women playing a card game, then the sentence X plus Y equals 4 is true for the following models. Like if X is 4 and Y is 0, X is 3 and Y is 1, and so on. So then all these models, yeah, so these would be possible models of the system. Okay, so what is then satisfaction? If a sentence alpha is true in the model M, we say that M satisfies the sentence alpha. We use the notation capital M of alpha to mean all the models that fulfill alpha. This is useful in the next definition. This is about entailment. So entailment is the relationship between two sentences. So if it's written like this, so alpha entails beta, so it's kind of a P that fell to the left. So we have here that if alpha is true, then beta is also true. And this is something that always holds. And then we say alpha entails beta. And then formally, you can define entailment as follows. So this is basically explaining. So this is the syntax kind of, alpha with the strange symbol beta. And what is the semantics? The semantics is that this is true alpha entails beta if and only if all the models for which alpha holds, so the models for which alpha holds is a subset of the models for which the statement beta holds. And that is kind of clear because if all the models for which alpha holds are included in the models for which beta holds, then of course, if alpha is true, then also beta has to be true. So as an example, the sentence x equals 0 entails also the sentence x times y equals 0. No matter what y is, this is always true. And that is because all the models for which this is true, this could be any y and x has to be 0, then the model for which this is true is also that x is 0 and y can be anything. Could also be 0, but doesn't have to be. And that's why this is entailed. Yes, the question is, does entailment simply mean implication? No, and because this is a standard question, we will discuss this aspect on the later slide. But it's a very good question. Okay, so first of all, we need to get a little bit more familiar with this concept. So let's look at an example. So let's say we started in room 1-1, and then we moved to room 2-1, where we feel the breeze. Then we want to know what are possible models. And we don't know what is in these rooms that have this black thick line or this black thick border. And of course, in each of these rooms can be a pit or not. And since we have 3 rooms, we have 2 to the power of 3 equal 8 models. So here you see all possible combinations. Okay. So the model wants to know whether the adjacent squares contain pits. So the knowledge base tells us, okay, only the only models that are true are those where pit is next to the breeze. So here you have a breeze, you have a pit, you have a breeze, you have a pit, or you can, in both of these squares can be a pit. All the other models are not true. So the pit is here, although there was no breeze here. So these are all incorrect models. Okay, so now we want to check the sentence. There is no pit in 1-2. 1-2 is this square here. So now we have to look at all the models for which this is true. So there's no pit here, 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 here. And for all the other models, this statement is not true. And what we can now see is that the models for which alpha 1 is true is a superset of the models for which the knowledge base is true. So as a consequence, we can say, given the knowledge base, we can entail that alpha 1 is true. So meaning we have proven there is no pit in 1-2 given the knowledge base. So this is what we've achieved just now. Okay. If we have another sentence like there is no pit in 2-2, so this is 2-2, this is true in these models, then you can see that the models for which alpha 2 is true is not a superset of the knowledge base. And because of that, the knowledge base does not entail that alpha 2 is true. So this is a statement that we could not prove. Okay. So now let's talk about propositional logic. So propositional logic, of course, is a specific logic. And we first introduced the syntax, and afterwards we introduced the semantics. Most of you are anyways familiar with this kind of logic. So in German is Aussagenlogik. Okay. So the propositional symbols S1 and S2 and so on are sentences. So if these are sentences, then you can also form a new sentence by negation. So if S is a sentence, then this symbol with in front of S is a sentence, which will be called negation. So what this means, we will discuss later on, although for propositional logic is quite straightforward. If S1 and S2 are sentences, then S1 with this kind of tent, S2 is a sentence, and this means conjunction. So the meaning will be and, so that if this is only true if both are true. If S1 and S2 are sentences, then S1 or S2 is a sentence, which is called disjunction, where you kind of invert this tent. And if S1 and S2 are sentences, then S1 with the right arrow, S2 is a sentence, which is an implication. What this means we will also discuss. By the way, this and or, some people also use different notation. This is the notation we're using in this lecture. If S and again, if S1 and S2 are sentences, then the arrow in both directions is also a sentence, which is called a biconditional. And you can also write this in short in Backus-Nauer form. This kind of form is used later on also in first order logic. It just says, okay, that any sentence can be formed as follows. So you can start with an atomic proposition. You can negate a sentence. You can have a conjunction, disjunction, implication, bicondition, or you can put parentheses around the formula to indicate preference, operator precedence. And the standard precedence is in descending order: negation, conjunction, disjunction, implication, and bicondition. Okay, so now we can play a small game and ask ourselves whether this is a correct formula or not. So the first formula is just true. So this is a little bit, maybe it's too easy to judge for some people, but you could, true is the same, for instance, as S or not S. And this is always true, this formula. And of course, S or not S is also a formula that is correctly formed. So we can say true is a correct propositional logic formula. So the next one here, is this a correct formula? I mean, you can just type yes or no. No, yes, that's correct. Why? Because you can only put a parenthesis around a correctly formed formula, and S1 is not a correct formula, so this is not correct. S1 implies S2. Again, can you say yes or no? Yeah, that's also not correct, because you can only use one arrow. Negate, no, not S. Is this? Yeah, everybody says yes, that's correct, because you can negate, and that's a formula, and then you can use negation again. This is also correct. S2 implies S3 is a correct formula. You can put this in parentheses according to this rule. And S1 implies another formula, is also correctly formed. And this one is not correct, because you cannot put negation in front of an incomplete formula. So negation can only be put in front of a correctly posed formula, and implies S2 is not a propositional logic formula. This is S1 implies not S2 is okay, because not S2 is propositional logic formula, and S1 implies a propositional logic formula is also okay. Okay, so now let's talk about the semantics. It's actually quite easy. Each propositional symbol can just be true or false. And if not S is true, that's the case if and only if S is false. S1 and S2 is true if and only if both are true. S1 or S2 is true if and only if one of them is true. S1 implies S2 is true if S1 is false or S2 is true. Another way is you can say this is a false formula if and only if S1 is true and S2 is false. Implication is the most complicated one, so we'll discuss this briefly on the next slide. And the bicondition is true if the implication in both directions is true. And you can now use these formulas to evaluate this step by step. So let's say P22 is false, P31 is true. So true or false is true. And then if P12 is true, true and true is true. So overall it evaluates to true. So this is what I've discussed. Now regarding the discussion, what's the difference between entailment and implication? So implication says, okay, if S1, for instance, is true, then also S2 is true, but it's also true if S1 is false, so if the premise is false. And the difference is that P entails Q if and only if the sentence P implies Q is always true for any model. So this, if only if the implication is a tautology, then we have an entailment, and otherwise we have an implication, because an implication, depending on the values of P and Q, can be true or false. That's the difference between entailment and implication. Okay. So now you can easily form these truth tables. So you have all combinations of P and Q. So not P is just everything negated. So it's true, true, false, false. P and Q, this would be false, 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 true, and so on. Yeah, this is really just a table that you can easily obtain based on the semantics. We can also use this table to explain the semantics because they are equivalent. Just again, a short discussion about the implication. So all assignments are intuitive except implication, as I mentioned. So the sentence 5 is even implies Tokyo is the capital of Germany. So we can do a spontaneous tweet back. So please mention whether you think this formula is true, or then you say yes. And if you think it's false, then say no. So yeah, just please use the tweetback so we have an overview of the feedback.
So about 85% thinks true.
Yes, that's correct, because 5 is even is false, and that's why the sentence is already true. So you can think of implication as P implies Q is as the same as if P is true, then I am claiming that Q is true. But if the premise is false, then the conclusion, of course, can be anything, and the statement is still true. So that's the only one, if you haven't worked a lot with logic, which is a little bit unintuitive if you at the beginning, but when you work with it, it makes a lot of sense. Okay, so now we can apply this to the Wumpus world. However, this takes some time, and the first 45 minutes are almost over, and we need some time to switch. So then I would suggest that I stop here, and now we can use what we've learned on the Wumpus world and see how you can automatically obtain new knowledge and make sure that you survive. Okay, good. So thanks a lot for joining. Also, thanks a lot for participating in the tweetback polls and also in the chat. I wish you a nice weekend, and then see you again next week. Okay, bye.
Again. All right, perfect, thank you. So yeah, then hi everybody, welcome. Good Friday afternoon, and welcome to the second exercise session for AI, which will be now for the first, let's say, major topic block in our AI lecture, namely for search and specifically for uninformed search. So again, as last time, the exercise sheets are uploaded to Moodle, so you can find them there, and the solutions will be uploaded then this evening after the exercise. Now there was just one question in tweetback regarding the programming tasks. So the programming tasks will probably start end of November, so in about maybe 2 to 3 weeks, but we will notify you about the programming tasks on time on Moodle, so about the start and the deadlines and so on. Okay, good. Then let's start. Again, like last time, we're just going to take a couple of minutes in the beginning before we start with the problems, and try to just revise some of the important things from the lecture, since it's already been a while since Professor Althoff has held the lecture on uninformed search. So basically last time we talked a little about how intelligent agents can be designed to solve real-world problems, and what we want to look at today is basically one major technique which can be applied to solve a problem, and which is actually a pretty intuitive technique. So if you have a problem and you want to find a solution to that, what you do, you start searching somehow for a solution, and in search we call this solution some kind of goal that we define. So that basically also brings us right into how a search problem is defined. So basically a search problem is defined by 5 major components. So the first component is some kind of initial state. So that's where we start off at for our search. Then we have defined some kind of actions that we can take. So we have some kind of action space, which depend on the specific problem we have. We have some kind of transition model, which tells us what exactly happens when we perform an action in a certain state. Then we have some kind of goal test that we define. So as I said, in search, we define a goal region or some goal we want to achieve, and we have to test whether we achieve this goal. And we also have path costs in certain search problems. So they tell us how, we could say expensive or how good or bad a certain path in the search is. Now, a search tree. So once we run a search algorithm, we obtain a search tree. And it basically contains 4 major components that are important. So we have some kind of root, which is the initial state. We have branches, which correspond to the actions. We have nodes, which represent the states that we've reached already. And we have so-called leaves, which correspond to unexpanded nodes. And what we can also define based on these 4 definitions in a search tree, or 4 components in a search tree, are 3 also important notions that we're going to use when we look at search algorithms. So it's once the frontier, which is called the open list. So the frontier basically contains all leaves that are available for expansion at the current state of the search. What we also have in certain search algorithms, not all, is a so-called explored set. So it's also called a closed list. These are basically all the nodes that we have visited already, that we have expanded. And finally, we also have a so-called queue. So a queue is basically what is the type of data structure we use for our frontier. So it's more or less, it defines in which order our frontier is sorted. And we have different variants for queues that we can use. So the 3 most important variants that we are looking at are first in, first out, which is, for example, used in breadth first search. We'll get to that later. Last in, first out, which is, for example, used in depth first search, and the priority queue, which is, for example, used in uniform cost search. Let me just check if there's some questions so far on tweetback. Okay, somebody asked what type of app I'm using. So the app is called Explain Everything. I think somebody asked that last time already. So it's called Explain Everything. It's a app. I think you have to pay for it. I'm not quite sure. Somebody asked how are search algorithms related to agents. So it's basically a technique that agents apply to solve a problem. One of the techniques. So search is one of the techniques, and what Professor Althoff started today, logic, is also another technique, and you'll get to know a few more then as the lecture proceeds. Okay, so then we can continue. So basically what we've also looked at are performance measures. So performance measures define or are basically criteria to measure how good a problem-solving algorithm or a search algorithm in this case is. And we look at 4 major criteria. So first of all, completeness. We want to know, is this algorithm guaranteed to find a solution if we know that the solution exists? Optimality. So optimality always refers to something with cost. So basically, we want to know if our strategy or algorithm is able to find an optimal solution. Optimal solution means optimal regarding to some kind of cost we defined beforehand. Then we have 2 criteria regarding or referring to the complexity of algorithms. So basically time and space complexity. Time complexity basically looks at how long does it take to find a solution, and space complexity looks how much memory do we need to perform the search or to find a solution. And these are basically essentially two very important measures when, for example, choosing an appropriate hardware for our search algorithms. So time complexity would somehow tell us what kind of CPU do we need. Space complexity would tell us how much memory, so how much RAM would we need to implement this algorithm. Okay, so the last thing I want to quickly talk about are classifications of search algorithms. So for us now, we are looking at 2 major classifications. First of all is tree search versus graph search. And this actually really refers to tree search versus graph search actually really refers to how we handle nodes that we've visited already. So in tree search, we are able to revisit nodes that we've already explored in the past. This gives us, No. So basically what this means that this gives us a good space complexity, so we don't have to store much of anything. However, it could be that our time complexity is very bad. Why? Because a tree search algorithm, since we do not remember what we visited before, may get stuck, for example, in infinite loops. And this can even happen on very simple search problems. In graph search, however, we remember the previously expanded nodes and we store them in the so-called explored set, which I've showed you two slides previously. And this means, oh, wait a second, I think it's cut off, so now it's better. So this means basically that we can't revisit previously expanded nodes. This gives us a good time complexity, so we avoid infinite loops. However, our space complexity is of course worse because we have to store additional information. We have to keep this explored set, which is an additional memory, which we need additional memory for. Now, the second classification we do in this lecture is basically the high-level classifications of algorithms for uninformed and informed search. So today we're only going to look at uninformed search. Uninformed search, you can basically think of, it's kind of like a blind search. So you don't use any additional information apart from the provided problem definition. So apart from, let me go back 2 slides, this here, this first point. So what defines our search problem? Examples for uninformed search that we're going to look at today are breadth first, depth first, and uniform cost search. And in informed search, you can think of it, it's a little more an intelligent way of searching. So intelligent means in this case, we try to estimate how promising a state is to reach a goal. And the way we do that is we have to define certain heuristics, which are problem specific. So we have to define them. And these heuristics are supposed to estimate how good our current or how promising it is that we can reach the goal from the current node we are at. Examples are, for example, greedy best first search and A star, which we are going to take a look at next exercise. Okay, then let me check if there were some questions. So will we go through exercise 2a or 2b? We'll only go over exercise 2a today. DFS and BFS, both tree or graph search. Yes, you can implement both algorithms, breadth first and depth first, as tree or graph search. And with tree search, if we go into an infinite loop, no, it won't. Would we? So the question was, if we go into an infinite loop, would we use up a lot of memory? No, we wouldn't. We would just lose a lot of time. We don't have to store anything extra, but we would just continuously just lose a lot of time and eventually get stuck in an infinite loop. Okay. Yeah, so these are basically, I just posted 2 of the algorithms that we're going to look at today. So we are not going to go through them in detail. It's just that if we want to jump back and if there are any questions, then we can take a look at the search algorithms. So for breadth first, there are just 2 things I'd like to highlight, which are important for today. So the first thing is the frontier is always a so-called first in, first out queue. So the node that we put in our frontier first also gets chosen first later when we choose a node from the frontier. And the second thing in breadth first search that's important is that we perform the goal test when we look at the childs of a node. So we don't select a node and then perform the goal test. We do it the other way around. We have a node, we look at the children of the node, and for each of these children, we perform a goal test and check if it's our goal node. And for uniform cost search, I'd like to just highlight the 3 major changes that we have compared to breadth first search. So the 3 major changes are: once we use a priority queue instead of a FIFO queue, so a first in, first out queue. And in this case, priority queue means we sort by the cost of the path. The second thing is that we do the goal test, not at the end when we select a child, but when we select the node that we want to expand. So once we select the node from the frontier, we do the goal test. In breadth first search, we did it when we look at the children of the node. This is an important difference between these 2 algorithms. And the third change is that we add a test at the end. So basically, we add the test if a child of a current node is already in the frontier with a higher path cost. If it is, then we replace it. The reason is that we always want to keep the frontier with the nodes that have the lowest cost. So we modify the frontier if we see that there's the same node in there that has a higher cost. Okay. Good. Then I guess we can start with the first exercise. So the first problem, which is problem 2.1. And we're just going to go through that now. So problem 2.1 is basically this graph that we're looking at here. And we say we want to start from A. So this is our initial node, A. Our goal node is F. So we want to reach here somewhere. And we have path costs. So I'm sorry, I think it's cut off again. Let's see if I can make it a little. Yeah, I think like this is good. So our path costs are shown here, basically on the arcs. And what we also do is we say, if there's no clear preference which node we want to explore next, then we will explore the node which is first alphabetically. So for example, in breadth first, if we have a first in, first out, but there is no clear decision which one was first in or first out, then we use an additional condition. So we use this alphabetic order of the nodes. Okay, so then the first question was to perform breadth first search. Again, I'll have to make it smaller here again on this graph. And what's also important, I think I'll jump back once again, is that we said we want to use graph search. So what does graph search tell us? Every time you read, you have to use graph search. Actually, it should ring a bell. That means you're going to use some kind of explored set. So you're going to store the nodes that you visited already. Okay, good. Then let me switch my pen here quickly, and we can start with breadth first search. So what we, one second, I have to, somehow my, got a little dark. Okay, sorry about that. Okay, so we're going to start with breadth first search. So the first node we're going to look at is obviously the start node, which is node A. So we're going to put in node A here. Now, what does our frontier look like? Maybe somebody can quickly write that in the chat, just to take a look if you've already thought about it. Yeah, BCD is correct. Exactly. So our frontier are basically, we add the child nodes of A to the frontier, B, C, and D, as we see it here. So we have B, C, D. We don't consider any costs because in breadth first search is not optimal, so we don't look at any costs. So, and our explored set, what does it look like? This maybe you could also quickly write in the chat. Just type, yes, exactly, A. Okay. All right, then which node are we going to select next? Let's just do the first step together. Next node is B, exactly. So B, why? Because we use, first of all, a first in, first out queue. And in this case, we said all of them, it's basically a tie between these three nodes. So we're going to use the one that's alphabetically first. So our frontier is going to look like the following. So we have CD left from the previous step, and we add the child node of B, which is E in this case. So we have a CDE as our frontier. And again, as previously, our explored, yes, exactly. Somebody wrote in the chat already, very good. It's A and B. Okay, the next step, I think that's pretty much the same. So I'll just do it quickly myself. So frontier, we pick the first node in the frontier, which is C. We look at child nodes of C. We see that C does not have any child nodes. So we just keep the frontier from the previous step, D and E, and we add our current node to the explored set, A, B, C. Okay, then next step, also pretty basic. Again, we look at our frontier, we pick the first node, D. We look at yeah, so what we do now, so basically how does our frontier look? That's not, so somebody asked why are we not keeping track of the costs? First of all, we don't keep track of the costs because we don't look at costs in BFS. Yeah, exactly. Sorry, 1 second. Somebody asked on Twitter, why for node B does the frontier include D? So yeah, for B, the frontier includes D because we obviously have to keep the frontier from the previous step. Okay, then let's jump back to node D again. So what is the what does the frontier for node D look like now? Okay, somebody wrote EF. So this was kind of like a trick in the end. It's actually only E. Why is it only E? Because let me jump back to the slide. That's what I wanted to show you before that. Basically, our algorithm terminates as soon as one of the children of the explored node is the goal state. So we do not even add this child to the frontier because, as you see in this line here, we pick the child, we perform a goal test, and then our algorithm terminates basically. So we return the solution directly here. So basically what this means is that our frontier only includes E. Our explored set, what does it look like? Maybe you could quickly type in the chat. Yes, exactly, A, B, C, D. Okay, yes. And exactly as somebody said, our goal node is F. So in this case, I'm sorry, this got a bit wrong scaled again. So now our goal node is F. So as soon as we're at D, we see a child node is the goal node, and that's where our algorithm terminates. And this is then basically the result of our algorithm. So we have 4 steps in breadth-first search. Okay, so somebody wrote on Tweetback why we started differently with the table. Professor Alto started differently with the table. He started with empty, explored, and A in frontier. Okay, yes. So basically, this is step 0, what you're talking about, the initialization step. This we omitted here in this case. Good that you asked that. Maybe I forgot to say that. So in this case, we omit the initialization step and we start directly with the first step where we have selected the initial node already. We're in the exam, for example, we're going to make this clear, obviously, at which step you're going to start. Okay, good. So then we have our solution for breadth-first search, and I guess we can continue with the second exercise, which was the same thing, just using depth-first search. Okay. Yeah, then let's start with depth-first search. So again, we don't write the initialization step, so we just start with the first node, which is A. And in this case, we always add the depth, the current depth that we have in a bracket after the node. So the first node is A, initial node, and we are at depth 0. Okay, so now who can tell me what the frontier looks like in this case again? Just write it in the chat. You can take a look. Yes, exactly, it's BCD. And in this case, we're going to always write the depth in brackets. So BCD, depth 1, because we're at level 1 of the search tree. Explored set is pretty simple. We are in node A, so we have visited node A. All right, next step. What's the next node that you're going to select? You can write it in the chat. Yes, exactly, B. So we select node B. We are at depth 1. And what does our frontier look like now? Yes, exactly. So basically ECD. I'm going to write it a little differently here now. Wait a second. I'm going to write it in this direction like that. The reason I'm going to do that is I'm going to tell you right now, because I just want to make it clear that we're using last in, first out now. So basically depth first search means last in, first out queue. So I just want to write it like that we can pick the last node, which is in our frontier, and then choose it as the next node. So this is the only reason I'm going to do that. So then our explored node is going to look pretty simple, just A, B. Okay, so next node, what's the next node? Somebody can write that in the chat, please. Yes, exactly, E, so last in, first out. E is the last node in the frontier. We're going to pick E, which is at depth 2 of the search tree, as you can see in the right figure. Okay, so then what does our frontier look like? Pretty simple in this case. We don't have any child node to add, so we just have C1 and D1. And explored set, also pretty simple. That's actually very basic, A, B, E. Okay, good. Then next step, pretty simple in this case. What do we choose? Okay, yeah. So 2 people wrote C, 1 person wrote D. It's actually C. Why is it C? Because both nodes have the first depth. We said in the exercise that if they have the same priority, we choose the one that's first alphabetically. Yes, exactly as somebody said. So we're going to choose C1 as the next node. We look at the graph again. We have no child, so it's basically D1, the only one that's left in the frontier. And our explored set of nodes looks like that, A, B, E, C. Okay. Then we have the next step. So this is now very simple because we only have 1 node left in the frontier. So we just choose the only node that's left in the frontier. Now, again, who can tell me what the frontier looks like? Remember what we've said before? What does the frontier look like? Yes, very good. So 1 person said empty, some people said F. Okay, most people said empty. So we're just going to write it like, wait a second, I'm going to use the symbol for empty set. So that's basically just means it's empty. And why is it empty? Because we see the child of D is already our goal node. So essentially our algorithm terminates here already. So we have our explored set A, B, E, C, D, and we're done basically. So somebody asked, why didn't we choose D first in the second pass since it's last in, first out in the second pass? Okay, yeah, maybe I didn't explain that there. Yes, it's basically because all of them have the same priorities. All of them have depth 1. And then we said we use the alphabetical order. This was what the problem statement basically said. So I think I forgot to say that here. So thanks for reminding me. Okay. Then I guess we should proceed to the next task, which is uniform cost search. So here in this case, again, as a reminder, we use a priority queue. That's one of the major differences. So we sort according to cost. Now we're going to use the cost, in this case, the first time. So this time what we're going to do is we're going to write the node, and in the brackets behind that, we write the cost. So I'll just start with the first node, A0. So I think maybe I'll just add it here that cost in brackets, that there's no confusion with the previous exercise. So, okay, so 0 is our cost in this case. Why is 0 our cost? Because it's our initial node. Very, very easy. Good. What does our frontier look like? So I'll just write it down. It's pretty simple. Frontier is B1. Somebody wrote it in the chat already. It's B1, C2, and D4. And our explored set is A because we're currently in node A. Okay, which node do we choose? Somebody can tell me? Yes, exactly. We choose B because we use a priority queue. So we choose the one with the least cost. So we say B1. Now we take a look at the graph again. So B1, our children node, let's just maybe highlight it. We have this in our frontier already. We have D in our frontier, and we're going to add E in our frontier. So basically, we're going to sort it according to cost again. So it's C2, it's E3, and it's D4. And we have our explored set, which is AB. Okay, then I'll just continue. It's basically the same thing like before. C2, we pick the one with the least cost. We take a look at the children node. We don't have any, so we just keep the frontier from the previous step. And we add C to our explored list or closed list. Somebody asked why E3, because we use the the whole path cost. So we use 2 + 1, which is 3. Yeah. Always the whole path cost, not the arc costs, basically. Okay, good. Next step, again, use the one with the least cost. So we have E3. We check there are no children of E, so we just can keep D4 in our frontier, and we add E to our explored list. Okay, next step is even simpler. We only have one node left in the frontier, so we say D4. We take a look at the, yeah, okay, this would be a question for you again in the chat. So what does our frontier look like this time? So somebody said, most people say F. Yes, this is correct. We have F, and in this case, the reason is because we do in uniform cost search. I can jump back some slides again to take a look at it. We don't perform the goal test when we look at the children. We perform the goal test once we've selected the node. So this is the major difference compared to BFS and DFS. And that's why we have to add F to the frontier first. We don't know yet that this is our goal region or our goal node. Okay, then we can say A, B, C, E, and we add D. And the next thing is pretty simple. So we have F5. What's our frontier look like now? Somebody can write in the chat. Yeah, it's again the empty set, no frontier. And yeah, we have basically we have reached our goal. So we can just say A, B, C, E, D. In this case, let me jump back to the algorithm once again. We do the goal test, and our algorithm terminates. So we don't add the node to the explored set. So the node gets added to the explored set after the goal test. So basically, since we know that this is our goal now, we don't add it anymore to the explored set. This is also very important in the algorithm. Okay, somebody asked, is the order of the explored set important? So it's just ordered by what you explored first. So we just always add it to the end. We extend it at the end. Is uniform cost search approach the same as Dijkstra's algorithm? Yes, it's similar. It's the same as Dijkstra's algorithm. We also wrote this on the lecture slide. Okay, good. Then I think we can finish this exercise. I think we got a pretty good idea about the different search algorithms, and we continue with the second one. We'll probably not manage it fully, but that doesn't matter because we're just going to continue next session. Okay. So in this exercise, we want to apply our search algorithm to a transportation problem. So we have 120 bricks, which we want to transport home. And I have to make this smaller again. So like this. And we have 3 actions. So we can take the bus, then we can transport 30 bricks and it costs 3 euros. We can take the car, then we can do 100 bricks and it costs 5 euros. And we can take the delivery where we can transport all the bricks, which costs 29 euros. And our initial node is S. Okay, so now there are first 2 things that we have to decide here. So first of all, what are we going to, what kind of algorithm are we going to use in this case? So tree search or graph search. In this case, it's important to define the problem. So yes, somebody wrote in the chat already, we're going to use tree search. Why? Because in this case, the actions that we have, so taking the bus, car, and delivery, they're not reversible. So they're basically one-way actions. And what this basically means is that once you've taken the bus and transported 30 bricks in this exercise, you can't untransport 30 bricks. So this action is just, it's not reversible. Like, for example, in other problems, like the Romania map problem, there is reversible. So this means that we can't have any loops in our problem. And in this case, it's good to apply a tree search algorithm. So this is the first thing. So we're going to use the tree search algorithm. And the second thing we're going to try to define is how does our goal test look like? So maybe this somebody has talked about already and can write it in the chat. So how, what is our goal test going to look like? Basically, how do we know we've reached our goal? Okay, n equals 0. Yes, I think you all mean the same thing. So it's basically number of bricks transported. So I'll just write it like this, number of bricks transported has to be greater or equal than 120, because then we know we have transported all bricks home and we've reached our goal. Okay, so then one more important thing, the way we're going to do it now is I'll just draw an example of how the tree search is going to look like. So we have an initial node S, and basically we have 3 actions. So we have bus, car, delivery. And what we do is we'll say that each node that we have corresponds to the action we take. So once we've taken the bus once, it's a B, C, and D. And now if we take the bus a second time, we're going to call it like this. So this is just for you to get to make this exercise a little simpler. So we say we are at the node BB, which basically means we've taken the bus twice. So this is basically how our search tree is going to look like. Okay, then I think we're ready to start. So we can start with the first exercise, which is basically a tweetback question. So Dao-E, maybe you could post the tweetback link again, and we start the poll. So the tweetback link, the question is in this case, if you want to make as few trips as possible, which search method should you use? Okay. So Dao-E, do you have a result already?
Yeah, so the majority chooses BFS, around 60%.
Okay, yeah, very nice. That's very good. So we're going to use BFS. What's the reason? The reason is that in BFS, we basically find the shallowest goal node. So we find the first goal node, and in our exercise, this corresponds to the least number of actions taken. So if the question is, if you want to make as few trips as possible, you don't want to take the bus, for example, multiple times. So you want to take the least number of actions, and this would be possible with BFS. All right, then let's look at what the search tree looks like. Then it's pretty simple. So what I'm going to do is I'm going to have the search tree on the right, and I'm going to have the node and cost on the left side. So we're going to do it like that. Node and cost. And we're going to look at the frontier. So why don't we have an explored list like in the previous exercise? Because we said we're going to use tree search in this case. Okay, so search tree is going to look like that. S, we have 3 actions. We have the action B, we have the action C, and we have the action D. And I will not write the costs here now first, because it's not so important in this case, but we'll try to see how our list looks like, our steps. So our first step is we're starting in S0, and our frontier with costs, maybe somebody can tell me what it's going to look like. Okay, yeah, okay, 3529, somebody said. It's almost correct. I think most people still add D. So in fact, so you're almost right. In fact, it's going to look like this. I'm going to tell you why exactly. C5. And that's it. Why don't we add D? Because D is essentially our goal node already. So I'm going to highlight this here. D is basically our goal node. Let's take a look why it's our goal node. Because we see that we can transport all the bricks with the delivery service. So this basically means that this is already our goal node and our search is done. And if you remember correctly, that if you remember correctly, so wait, I'll just add the costs here still quickly. So if you remember correctly, in BFS, we our algorithm terminates as soon as we find the first goal node. So as soon as we find that the child of S is a goal node, we terminate and we don't add it to the frontier anymore. So somebody said BFS disregards costs. So yes, we don't use costs in this case. The only reason I added costs here was because the question was, okay, sorry, this is not written in the question. So we basically always want to find out for the different algorithms what the resulting cost would be theoretically, but we don't use the cost. So in this case, if we use BFS, our goal node is D, and we say, so our goal is D, and our resulting cost, so it's going to cost us 29 euros. So yeah, this maybe I should have said that before that. So we always want to know, we want to compare the different costs, so what it's going to cost in the end when using the different algorithms. All right, good. Then we continue with the next exercise. Let's see if we get that done. And it's again a tweetback question. So in this case, the tweetback question is, if you want to minimize cost, which search method should you use? Okay, you can just vote in tweetback again.
Yeah, for now, I see almost all people chooses uniform cost search.
Okay, yeah, very good. So that's also the right solution. So you're going to use uniform cost search. Why? Because it's the only algorithm that we have for that, or that we've learned now for uninformed search algorithms that basically considers cost. So the only optimal algorithm. Okay, somebody asked in the chat if I can go back to the last slide. Can I make the same example, assuming delivery? Can take half of bricks. So somebody asked if I can make the same example, assuming with delivery that I can take half of bricks. That option, the goal DD, so I would have to check it out. So I think this is a bit hard to say. In this case, one would have to just define the problem new. It could also be that in this case, the car would be the best option. So it's a bit hard to just say it now to modify the problem. We would just have to draw a whole tree new. So if you want, you could ask this question in Moodle again, and then I can try to upload the solution for this for this modified problem. Okay, then I think we can start. So unfortunately, we don't have too much time, but we'll just start with the problem, and then we'll continue next week. So again, we're going to write here node and cost and frontier with cost. So same as in the last example. Okay, and here on the left side, we're going to, we're going to have our search tree. Okay, we start with node 0. We have 3 actions. 3 actions basically mean B, C, D. So our frontier contains B with cost 3, C with cost 5, and D with cost 29. So if we draw it like this, I have to draw it a little differently because I need space here. So we have C, B, and D. And 3, 5, 29. All right. So who can tell me what the next node is that we'll be expanding with uniform cost search? Yes, exactly, B. So we have B3. Again, we have 3 actions. So we can expand our tree like this. So BB, if we take the bus twice, we have BC. And we have BD. Yeah, somebody mentioned we should add the bricks left. So basically, yeah, this is just for simplification purposes. We said it's easier to read the graph if we say we take the bus twice. So you can say twice the bus means we've transported, I have to check if 60 bricks, I think. Yes, 60 bricks. So we have 60 bricks left. The problem is if I write the nodes such that we write the bricks, the number of bricks left, then we would just have numbers here and it would be a little difficult to read in my opinion. So in this case, we just say, okay, the nodes correspond to the letters and the letters correspond to the actions that we've taken so far. Okay, so we have 3, 5, and 29 again. Now our frontier, we sort the frontier again according to costs. So what we're going to do is we're going to say C5. Oh God, my handwriting, sorry. C5 is the least cost. The next one is BB, which is 3 plus 3. So BB, which is basically 6. The next one is BC, which is 3 plus 5. That's 8. The next one is D from this example, from the previous step, which is 29. And the last one is BD, which is 32 in this case. Okay, so I'm going to make like a line here that we can separate it better. All right. Good. Next node we pick again. We have ordered our frontier already, so we just pick the first one in the frontier, which is the least cost, C5, and we do the same thing. So we pick C, we expand C again with 3 actions, CB, CC, and CD. So, like this. 3, 5, 29. Okay, somebody asked in tweetback if we always have to create a table like this in the exam. So of course in the exam we'll tell you if you have to create a table like that. We are just doing it here for to keep an overview a little about that. So yeah, this of course we'll say in the exam if you have to do that. Okay, then we'll just do the last step. So just bear with me 1 minute or so, and then we can finish for today. Otherwise we'll extend the session too long. Okay, so we'll just write up the frontier for the next step, which is choosing C5. So again, we chose C5, so we add BB from the last step, which is 6. We have BC, which is the next one, which is 8. Then we have CC, which is 5 plus 5, so 10. Then we have D from the previous step, which is 29. We have BD from the previous step, which is 32. And we have CD here, this node basically here. And this is 29 plus 5, which is 34. Yeah. Okay. So we've still not reached our goal because we still didn't transport all the bricks. But for now, I think we'll just finish and continue next week with the same exercise. So then somebody asked, what about CB? CB. Ah, yeah, right. What about CB? So we said that we're going to say CB and BC is basically just the same. So we're not going to add it in the frontier because the order doesn't really matter. Okay. Good. Yeah. Then, as I said, we'll continue next week with the exercise. And first of all, thank you all for joining today, and have a nice Friday. Have a nice weekend, and see you next week. And I'll still stay here a little to answer some of the tweetback questions. But yeah, if you don't have any questions, you can also just leave. So yeah, this rest will be recorded till the last 5 minutes. Okay, bye-bye for anybody who wants to leave. And